So my talk will be about the different ways how we can use the knowledge of symmetries present in datasets in order to improve machine learning systems. So I finished my PhD this year, 2022, and until now my work was mostly in applications. So this talk will be also about applications, mostly in computer vision. So I haven't seen the previous talks, but I guess the previous talks were mostly about mathematics. This will be more about applications. So the talk will be, here is the outline of the talk. First, I will speak about motivation. I will speak about current state of machine learning research, which is very much focused on scaling computation, scaling data sets, which is very expensive. And this motivates us to develop some other approaches which are not that expensive. And I will talk about 3 different ways how symmetries can be leveraged. The first way, very simple way, is called data augmentation. This is used to enlarge the training set. The second way is to remove the symmetry from the input so that the machine learning model deals with some simplified canonical representation. And the third way is to design models which are automatically invariant or equivariant to the symmetries, which we know that they exist in the data. So, okay, I need to move this. So you have probably heard about how machine learning is revolutionizing and all kinds of scientific and engineering domains. And you have maybe seen some of these amazing applications. For example, this I have here this image, which is output from a model which is able to generate images based on the text. So you dictate the text, and the model is able to produce the image which contains the content of the text. Here, for example, this is the picture from the famous movie, and here the user selected some part of the image. Here you can, I don't know whether you see the rectangle, but there is this rectangle, and then he dictated this text, you know, baby dragon perched on a pirate's shoulder, and the model generates the image, which seems almost like a magic that you can dictate almost anything you want, any crazy idea which probably never was drawn anywhere, and the model very often is able to generate the realistically looking image. And even the more surprising thing is that nobody understands what's going on inside these models. Nobody, because these models usually contain billions of parameters, so it's not explainable. You cannot look and see what the model is doing. So this is quite fascinating that we have these kind of models which we don't understand what they are doing, and yeah, and there is huge gap between theory and practice. I think this holds in many other fields, but especially in machine learning, there is really a huge gap. And often the practitioners who develop these kind of applications, they have very little understanding of the theoretical machine learning, because yeah, usually the ideas which we develop in theoretical machine learning are not very relevant to this kind of scaled or these kind of approaches which are designed by all kinds of ad hoc hacks, and usually the resulting model is not very analyzable, and it's often developed by trial and error process. So that's kind of unfortunate that we are in this state, but I think same thing holds for other fields too. So that's the current state of the research, and many people focus on scaling. You know, there is this famous blog post by Richard Sutton, who is one of the main figures in this area. The blog post is called "Bitter Lesson," and the message he tries to convey is that the bitter lesson is the fact that usually you can try to do all kinds of clever things, but at the end, if you scale the computation, you get much better improvements. So he suggests that instead of us trying to understand the problem and trying to design some clever algorithms, we should just focus on scaling and not to waste time by designing something clever, which is quite sad, because then the research becomes about who has more resources, because in order to train these models, you need a lot of resources. Usually, for the state-of-the-art models, like the one which I showed, which generates the pictures from text, usually you pay only for the electricity, you would pay millions of dollars. So this is not a research which some academic researcher would be able to do. So this is a motivation for other ways how we can somehow decrease the requirements for amounts of training data, amounts of computation, and this is where symmetries in the data come into the picture. So I will speak about this, as I mentioned, these 3 different ways how symmetries can be used. First is data augmentation. The second is removing the symmetry from the input. And the third is designing the network, the machine learning model, to be automatically invariant or equivariant to these symmetries. So first, as I said, I will be talking mostly about computer vision. And in computer vision, one of the obvious symmetries which exist there is the symmetry of translation. And we usually would say that we want our models for computer vision, for example, some classification model which classifies, here in this picture, the model should classify what kind of digit is present in the image. We want these models to be invariant with respect to translation. So if I translate the image, I want the model to produce the same output. By the way, do you see this panel, which
no, only the slides.
Only the slides. Nice. Okay. So this is translation symmetry, and the popular models for image computer vision are these convolutional neural networks, which are based on these convolutional layers, and these convolutional layers are designed to be automatically equivariant with respect to translation. But there are many other symmetries which exist in computer vision. For example, there is change of perspective, change of lighting, change of background, and many other symmetries which exist, but they are not leveraged by current neural networks. So there is a lot of opportunity to improve these models. So here I have a slide about like formally defining what we mean by symmetries, but I will not use this formalism later in the talks. This is just for completeness. So symmetries, we usually model symmetries as groups of transformations which preserve some kind of property of the given object. So we would like to speak about invariance and equivariance, and for that we need to speak about representation. So representation of a group G is a function from this group to a set of invertible matrices which has this property. So if we multiply the elements of the groups and then we create the representation, it should be the same as if we first create the representations of these elements and then we multiply the matrices. And then we can say that the function, here function L, which goes from a vector space X to vector space Y, is equivariant with respect to this group if the following equation holds. So it says that if we first apply the function L and then we apply the transformation, it should be the same as if we first apply the transformation and then we apply the function L. And here the transformation could be represented differently for vector space X and vector space Y. And the special notion of equivariance is invariance, and this is equivariance where the representation in the vector space Y is identity matrix. Then it means that the output of the function will not change if we apply the transformation. So this is the formal notion of what we mean by equivariance, invariance, and symmetries. And here, the first approach which I will be talking about is this data augmentation. So data augmentation is a very popular technique in machine learning, which is often used to increase the accuracy of the trained model. And it works by, you have some kind of symmetry, with, for example, translation or rotation, and you enlarge the training set by applying this transformation to the inputs or to the training examples. So here, if you see the image, these are all images which are created from one image by applying these different transformations. So it could be rotation, it could be change of brightness, and by creating this modification, we enlarge the training set, and then we usually improve the accuracy of on the testing set, because the model sees more, he sees the variations which can be present in the testing set. And the classical augmentations which are used for images are these very simple transformations like rotations, translations, change of brightness. But we can also model more advanced augmentations if we use, for example, rendering engines, which I will show you later. So here the motivation is that usually to obtain a large training set, usually this is the most expensive part of machine learning, of many machine learning projects, especially if there is no available data on internet. Then to collect a training set for supervised learning, where you, for every input, you need to also have some label, which usually some person needs to do. This is usually the most expensive part of machine learning project. So there is a huge incentives for eliminating this process of labeling the data. And for this, we can use these generative models. So if you would take a class in introductory machine learning, people would also usually think about speak about generative versus discriminative models. So we usually understand that we have some observed measurable data, which is here denoted by variables x. This is something which we measure by some measurement device. And then we assume that there is some hidden or latent variables which somehow caused these measured variables. And we would like to estimate these unobserved latent variables from these measurable variables. And this is done by this recognition model. The recognition or discriminative model, it describes this probability P of y given x. So condition on the observable variables, we get a probability for different configurations of latent variables. So here it could be, for example, the observables can be an image, and the latent variables could be the classes of objects which are present in the image. And then generative models, they are more, they contain more information, because they also describe the distribution of the observed variables. So here it describes the joint probability of y and x, which usually can be factored as p of y times p of x given y. And this is something. This is the generative process which describes how the observable data is being generated. And this is often the process which we can understand. We can have models, physical models, or other simulators which describe how the observable data is being generated, and this is very useful tool for expressing our domain knowledge. So if we know something about the domain, we can express this knowledge using these generative models. Here is some schema which describes this idea. So, for example, here is a person is looking at some scene, and we have these three components. One is the p of y. This can describe our understanding how for example, it can contain our understanding of physical some properties, like here how things move. Then we have this process which describes how the state of the world is being projected onto our eyes. So this is described by our knowledge of optics, how light is being reflected and how it travels to our retina. And then we have this third part, which is how our brain is able to reconstruct the scene from the measurement on our eyes. And this is something very complex which we don't usually understand. So usually we understand how this causal direction works. Here it's optics and other things about the world, but we don't understand how our brain is able to do this thing, that from the image we are able to reconstruct the latent description of the scene. So if we leverage our knowledge of what we know, we can create these simulators, and then we can view the recognition model as kind of as inversion of this simulator. So, for example, in computer vision, we can view computer vision as inverse computer graphics. And computer graphics is something which we very well understand. We know how to simulate light. We know how to create very realistic looking images. And so we can use this knowledge to help us in designing better recognition system or these discriminative models. So here, this was my first project which I worked on during my PhD. The idea was to use game engines which are used to very quickly simulate realistically looking images, to use these game engines to generate training data for neural networks. And we use this game engine called Unreal Engine, and we were able to generate millions of images in a day with all kinds of useful information. So, for example, here I can, for the same image, I am showing different kind of labels which we generated. So, for example, in the bottom left, here is an edge map. So here the pixels represent the edges present in the picture. Then on the top right, there is information for semantic segmentation, where for every pixel we assign a class of the object which contains this pixel, and this is basically generated for free because we know this. We have complete control over the generating process, so we can generate all kinds of labels like that, and then we can use it for training the neural network. What I also did, I used composed these rendered objects with natural scenes. So here I had a video with some background, and I placed into that video the object, and this creates very realistically looking images, which I can also control. For example, here I am changing the material of the object, so I was able to create a lot of different variations with this system. Another idea for which we use this synthetic generating synthetic for this framework for generating synthetic images was what we call compositional learning. And the idea is that if you look at a trained neural network, which is trained to recognize images, if you would inspect the filters in different layers, you would see that there are filters which are sensitive to different parts of the object for which the network is trained to recognize. So for example, if you train the network to recognize cars, you would probably find some filters which would be sensitive to wheels of the car. And so we can use this, we can help the network to train by forcing some features to automatically detect these parts. We don't need to wait until the network finds these parts by themselves. We can add additional labels. Instead of just having a label that this is a car, we can have additional labels which tell us that here is a wheel, and I want this filter to be sensitive to wheels, for example. And so what we did, we used this synthetic data generating framework to automatically produce labels for also these subparts. This would be very tedious to do by hand, to label these subparts on every image. But if you are generating the data synthetically, you can produce these labels very easily. So, and then once we had these labels, we add an additional term to the loss function, which penalized the network if some features which we selected in different layers, if these features were not detecting that these parts are present. And using this kind of training, we achieved the similar accuracy as if we would train the network only with the final labels, but the training was five times faster, because the search was more restricted by us forcing the filters to produce certain values. So this was the part about data augmentation. Then the second way how we can leverage symmetries is to remove the symmetry from the input. And if you think about the previous approach, this data augmentation, it's quite wasteful, because you want the final model to be invariant with respect to these variations, and for that you generate all kinds of possible variations of the input and train the network to basically ignore it. And it would be much better if you would start if the network could ignore these variations already. The input would be somehow, the variations will be removed. So this is the idea of removing the symmetry from the input by transforming the input into some canonical representation. So here you can see that if you have this image, you can make it to some canonical form where it doesn't matter how was the digit translated or rotated in the original image. So this is a very obvious idea, and we published this paper called semantic segmentation, segmenting out generic objects in monocular videos. And our original motivation was that we wanted to design an algorithm for unsupervised discovery of object categories. So the idea is that you would have a data set of images, and you would like to have an algorithm which automatically detects what kind of classes or categories exist inside this data set, and it will also be able to segment out these objects inside these images. And this is something which we as humans, we are able to do. So for example, here on the image on the right, you probably have no idea what kind of object it is. You don't know the class or the category of this object, but you are able to segment out. You would be able to segment out this object. You will be able to tell where are the borders of the object. And this is very different from the classical task, which is called semantic segmentation, where you have fixed number of classes, and the goal is to segment out the image to this to assign every pixel in the image to one of these classes. Here we assume that we don't know what kind of classes may exist in the data set, and we would like to automatically segment out these objects and then also be able to discover categories which are present in the data set. And then our idea was that if we remove the symmetry of backgrounds, which often take a very large part of the image, then we can use simple clustering algorithm to discover the categories as clusters in this data set. So here on the image in the bottom, you can see that there is this squirrel, but the background takes large part of the image. And on the top, you have the same image, but the squirrel is already segmented out. And if we then create some low-dimensional representation of this with some non-linear dimensionality reduction technique, then we obtain vectors which cluster well, which create meaningful clusters. Whereas if we cluster these vectors obtained from the non-segmented images, then the clustering doesn't make much sense, because the background is confused. The similarity is influenced by the background, and then the clustering may not make too much sense. So this was the idea. We wanted to segment out, remove the symmetry of here in this case of the background, and then we hope that the clustering would work. So here, what we did, for the clustering, we created a similarity graph of the resulting vectors, and then on this similarity graph, we used a community detection algorithm, which discovered these communities, and then we measured how precise the algorithm is by measuring whether we knew the ground truth classes of every image, and we measured how accurate is the algorithm if for example, same images of the same class were assigned to a same cluster. And if we do this by removing the background, then we achieve very high accuracy. But if the background is present and we use the same technique, then the accuracy is very low. So this is very simple idea, but the problem was how to remove the background, because that at the time when we were working on this, there were no working methods which would be easily applicable for background removal. So what we did, we created an ensemble of 3 different models, which are trained by 3 different objectives. So one model here on the right, this was a model trained for depth estimation, where the task is for every pixel in the image, you would like to predict how far is the object belonging to this pixel. So pixels which are very close to the camera, I have very high value here, for example, yellow or red, and pixels which are very far away from the camera has very low value. So here, for example, dark. And then if you have this kind of depth map, then you can segment out the object by discontinuities in this depth map. So this was first model which worked in some scenarios but failed in others where there was no discontinuities. So the second model which we used was the model for motion estimation, and this model works by predicting the movement of pixels. So this works only for videos. So if you have a video, you can, for every pixel, you can ask a question where the pixel will move in the next frame. And these motion estimation models are trained to predict this kind of movement. So it creates a vector field for the image, which tells where every pixel will move in the next frame. So this was also a model which worked in some scenarios where the objects were moving, but if the object is not moving, then the object then this model fails. And then the third model, which is very accurate, but it requires initialization, is a tracker. And this model, it also works only for videos. So if you have if you label some object by a rectangle in the video, then the tracker is able to follow this object throughout the video. So what we did, we used these first two models to initialize the bounding box for the tracker, and then the tracker was able to follow this object in the rest of the video. And then we use some kind of weighting score scheme to assign, to have some confidence about whether the object is really there or not. And from this, we were able to remove the background when these models agree. Then we are able to remove the background, and as I said, once you remove the background, the resulting task, for example, classification, becomes much easier. So this was the second approach, how we can leverage symmetries. And the last approach works by designing neural networks which automatically are invariant or equivariant with respect to these symmetries. So here, the main building block are graph neural networks. And these are neural networks which are designed to process graph structured data. So one feature which they need to take into account is that graphs, they have no natural order of vertices. So for example, if you work with classical neural networks, they process some vectorized inputs, and in the vector there is a fixed order of the components of the vector. But for graphs, there is no fixed order. So the neural network, or the graph neural network, needs to be invariant with respect to permutations of these vertices. Because you need to represent the graph as with some kind of order in the computer, for example, by adjacency matrix. Then if you permute the rows or columns of this adjacency matrix, then it will be still same graph, but there is this ad hoc order. So the network needs to be automatically invariant with respect to this order. And there is already a well-established field called graph signal processing, which deals with signals represented on graphs. So signal on a graph, by this we mean that there is an assignment of real value to every vertex in the graph. And once we have such a signal, we can then do very similar things which are done in classical signal processing, like for example applying Fourier transform, applying convolution, and do all kinds of things which we are usually doing in signal processing. So here the basic representation of graphs is this Laplacian matrix, which is computed by having this matrix D, which contains degrees of vertices on the diagonal, minus this adjacency matrix, which contains zeros and ones, and there is a one in the cell in the row, and there is a one on a set of a cell in the row I and column J if there is an edge between vertex I and vertex J. And so this is the basic representation for graphs. And then if you have such graph, you can do Fourier transform of the signal represented on this graph by doing eigen decomposition of this Laplacian matrix. So here for intuition, if the graph is this simple regular grid, then if you do this eigen decomposition and then you visualize these eigenvectors, because the eigenvector, it will have as many elements as there are vertices in this graph. So you can visualize these eigenvectors by coloring every vertex by the value of this element in the eigenvector. Then you can see that you, for this very simple graph, you will recover the periodic functions in the 2D plane. So this would be same as in classical Fourier transform. This will be like the two-dimensional sines and cosines. But if you change the graph, then the eigenvectors will have, you will not see this simple structure. There will be something else. But the idea is similar, that these eigenvectors will have the role of these sines and cosines, and then to do the Fourier transform, you would just project the signal onto these eigenvectors. So here is how you can do graph convolution, because it's not clear how to do convolution on a graph, because every vertex has different neighborhood. So you cannot have a fixed kernel. But we can use this idea that convolution in the Fourier domain, in the spectral domain, is same as is computed by multiplying the Fourier representation of the signal element-wise by some numbers. So how we can do graph convolution? It is done by projecting the signal onto the Fourier domain, then multiplying the resulting vector by some scalars, and then projecting it back to the graph domain. And in this way, you can do some kind of filtering of the signal on the graph. And so this idea was used for first graph neural networks, where we would just learn these coefficients of this convolutional operator in the spectral domain. We would learn these coefficients by gradient descent, as it's usually done in neural networks, and then we would project it. We would take the signal on the graph, we would project it onto these eigenvectors, then we would multiply the resulting signal by these coefficients which are learned, and then we would project it back, and we would say that this is one layer of a graph neural network. There is one disadvantage of this approach, because this learned filter will only work for a fixed graph, because if you change the graph, then these eigenvectors will change, and you cannot apply this learned learned coefficients. So later people did some approximations in order to do all this processing in the spatial domain or in the domain of the graph, not in the spectral domain, but in the original domain of the graph. And this is how these graph neural networks work like today. The idea is that you would have some kind of feature vector for every vertex in the graph, and then you would do this message passing. And the message passing works. You have for one layer of this graph neural network, you have one matrix of learnable parameters, and you would multiply these feature vectors by this matrix to obtain a new representation for every vertex. And then you aggregate, for every vertex, you aggregate the vectors of neighboring nodes. So here I'm showing the plus sign, which means that I'm just summing the vectors, the multiplied vectors of the neighboring vertices. And this is one layer of the graph neural network. Then we can apply some nonlinear activation function like this thresholding function, and we do multiple layers of these. We apply multiple layers of these, where every layer can have different matrix with learnable parameters. And then at the end, it depends what we want to do. There are two main tasks. One is that we can classify. We may want to classify the vertices of the graph. So, for example, if the graph is a social network, we may like where every vertex corresponds to a person. We may want to classify this person to some category. So this is node level classification. And then there are other tasks where we may want to classify the whole graph. For example, if we are dealing with molecules, we may want to classify the whole graph which corresponds to this molecule. And there we need to aggregate all the feature vectors from all the vertices to one vector, which we finally classify by some multi-layer perceptron or something like that. And the aggregation operator, the only requirement for it is that it's symmetric, because, as I said, there is we need that the whole network is permutation invariant. So this aggregation needs to be symmetric. So it could be a summation, it could be averaging, it could be element-wise maximum, or some combination of those. And then the resulting network is automatically equivariant or invariant with respect to permutation of indices. And one of our applications which we worked on was in 3D shape classification, where we have some representation of some object as this 3D mesh. And you can see that this mesh is a kind of graph, that the vertices, it has vertices and edges. So we can represent this object as a graph, and then we can apply these graph neural networks to classify, for example, these objects. And what we did in this application, or in this paper which we published this year, there were many ideas in this paper, but one which is relevant to this talk is that the graph neural network was automatically designed to be invariant with respect to rotations and translations of the object. So if the object is represented in different coordinate frame, then we wanted that the model will produce same outputs. And for this, we used these ideas which were published in 2018 in this paper called Tensor Field Networks, where the learnable filters are basically superpositions of these spherical harmonics, which makes the whole network the filters are constrained to be invariant or equivariant with respect to this group of a special Euclidean group which contains all 3D rotations and translations. And so here the idea was that, as I said, one of the symmetries which is present in images is change of perspective. So if we have a camera and we move the camera, we point it to the same object but from different angle, suddenly we have very different representation, but we would like to be automatically invariant with respect to this change. So here the one option is that there are today cameras which are able to produce these 3D representations, and then if you apply this graph neural network on this 3D representation, then you can automatically be invariant with respect to change of perspective. So here is the summary. So there are many different symmetries exist in computer vision data sets. And the idea is that if we remove them one by one, we remove all these symmetries, then the only thing which remains is some kind of essence for example, of the object. And then the task became much more simpler because all these variations are gone, and the classifier only needs to learn about the specific which somehow represent the semantic content of the image. And as I said, there are these three natural ways how to leverage these symmetries. One is to use these data augmentations. The second is to remove the symmetries from the input. And the third way is to design the networks to be automatically invariant or equivariant to these symmetries. So that's all from me, I think. Yeah, so that's all, and thank you for your attention, and we can now have discussion and questions.